Hi everyone, this is Dr. G. Ravindranath Reddy, working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that course, we are at the inverse Laplace transform of derivatives. So in this video, we are going to discuss how we can apply this inverse Laplace transform of derivatives to find out the inverse Laplace transform of the given function f bar of s. So first, before going to take the problems on this, first let us take the statement of this inverse Laplace transform of derivatives. So L inverse of f bar of s. So that inverse Laplace transform is applicable for f bar of s. So we can take L inverse, that is inverse Laplace transform of f bar of s is equal to f of t. Then inverse Laplace transform of f bar of n, f bar power n, this we can call it as a nth derivative. So we will read it as L inverse of nth derivative of f bar of s. Nth derivative of f bar of s is equal to minus 1 whole to the power of n into t power n f of t. So where this is represented with this nth derivative of f bar of s. So how can you prove this condition here? So whatever the formula we are studying in the inverse Laplace transform, so no need to prove separately. So we can take the help of Laplace transform formulas, and by using that Laplace transform formulas, we can convert into inverse Laplace transform of derivatives, inverse Laplace transform formulas. So now, whereas if you go for the Laplace transform, so first what we have to do is you send this L inverse to this side, so you will get this is equal to Laplace transform of t power n into f of t. So this is given by minus 1 whole to the power of n into nth derivative of f bar of s. That is, in order to prove this condition which we are studying in the inverse Laplace transform of derivative, so let take the help of Laplace transform of t power n into f of t. So while we are discussing the Laplace transform of f of t, whenever that f of t is multiplied with the t power n, so we have proved that condition, Laplace transform of t power n into f of t. So this is our formula, minus 1 whole to the power of n into nth derivative of f bar of s. So we can easily identify the formula in the Laplace transform, and by using that formula we can convert that Laplace transform formula in terms of inverse Laplace transform formula. So from this we got this formula, that is, suppose L inverse of, if you want to find out the first derivative of f bar of s, then we can replace n is equal to 1, we can get our required value, that is minus t into f of t. So this minus t into f of t, we can take that f of t, we can replace that f of t with L inverse of f bar of s. L inverse of f bar of s. And similarly, suppose if you want to go for the inverse Laplace transform for the second derivative f bar double dash of s, so then you can take minus 1 whole square into t square. Since the number of times we have applied the derivative is 2 times, so the 2 must be the power of t in the RHS side, and L inverse of f bar of s. So this is the formula what we have discussed now. L inverse of f bar dash of s, first derivative of f bar of s. For this, if you want to find out the L inverse, then we can take that value is equal to minus t into f of t. So that f of t can be written as L inverse of f bar of s. And similarly, for the second derivative, if you want to find out inverse Laplace transform for f bar double dash, that is second derivative of f bar of s, then this minus sign becomes a positive and this t becomes a t square and f of t, that is t square minus t square into L inverse of f bar of s. And similarly, if you want to find out L inverse of third derivative of f bar of s. So third derivative means 3 is an odd number, so we can keep minus sign. And number of times we have applied the derivative is 3 times, so we have to take t cube into L inverse of f bar of s. This L inverse of f bar of s is common for all these things. So like this, we can derive the formula for inverse Laplace transform of nth derivative. So we will get this standard formula. So by taking n is equal to 1, we will get our Laplace transform for inverse Laplace transform of first derivative. If we take n is equal to 2, we will get the inverse Laplace transform of second derivative of f bar of s. So like this, by substituting different values of n, you will get different formulas in the derivatives of inverse Laplace transform. Now we will see where we can use this inverse Laplace transform of derivative formula. So whenever the function is in terms of logarithmic function, so that is our given f bar of s is in terms of log, or in terms of inverse trigonometric functions like tan inverse or cot inverse, then whenever we are having f bar of s either in terms of log or in terms of inverse trigonometric function like tan inverse or cot inverse, then if you want to find out that inverse Laplace transform for these functions, then we can take the help of inverse Laplace transform of derivatives. That is the important thing we have to remember. Now let us take one by one how we can apply this inverse Laplace transform derivative for the logarithmic function, for the inverse tan inverse function, for cot inverse function. Now let us take the first, we will take the logarithmic function here. Find L inverse of log of s plus 1 by s minus 1. This is a logarithmic function here. So for this logarithmic function, we are going to find out inverse Laplace transform. So how can you find out this inverse Laplace transform here? Let us see. By using this inverse Laplace transform of derivative. So whatever the function he has given inside L inverse, we can consider this entire function as f bar of s. So let us take the function f bar of s is equal to the logarithmic function here. So once if you observe this one, this is of the form log of a by b. The given function is in this form log of a by b. So we have the formula log a minus log b. Use this. So this can be written as log of s plus 1 minus log of s minus 1. So now we got f bar of s is equal to, finally we got f bar of s is equal to log of s plus 1 minus log of s minus 1. So after taking this log f bar of s value, now immediately you find out the derivative of this. Apply the derivative with respect to s, ordinary derivative with respect to s on both sides. So you will get d by ds of log of s plus 1 minus d by ds of log of s minus 1. So this is of the form derivative of log x. So what is the derivative of log x here? We can consider that as 1 by x. So follow the same procedure here. So in place of x, here we are having 1 by s plus 1 minus, in place of x here we are having 1 s minus 1. So this can be written as 1 by s plus 1 minus 1 by s minus 1. This is f bar dash of s. Now you apply inverse Laplace transform on both sides. Apply L inverse on both sides for this. Now this can be written as L inverse of f bar dash of s is equal to L inverse of this. Both sides I am applying inverse Laplace transform. So now this can be written as, so what is the formula for just now we have seen in the previous video, we have seen L inverse of f bar dash of s is equal to minus t into f of t, or this can be written as minus t into L inverse of f bar of s. So that is the thing what we have taken here. So this is equal to, this implies, so this LHS part I have taken this minus t into L inverse of f bar of s. Now this can be written as, apply the linearity property, L inverse of 1 by s plus 1 minus L inverse of 1 by s minus 1. So this can be written as, directly we have the formula L inverse of 1 by s plus a minus L inverse of 1 by s minus a. Use this formula, you will get e power minus at minus e power at. So what is a here? 1. So you will get e power minus 1 into t minus e power 1 into t. This is our. But here we don't want this minus t here. So you send this minus t to this side. So you will get minus 1 by 2 into this one. So now replace f bar of s. What is the value we have considered for f bar of s at the beginning here? F bar of s is equal to this. So L inverse of f bar of s replace with this, we will get our required value here. So this is the way how we can apply this inverse Laplace transform of derivative to find out the inverse Laplace transform for the logarithmic function. This is the simple logic we have to apply to get the inverse Laplace transform of logarithmic functions here. And similarly, we will go for the next one. We will take some inverse trigonometric function, either tan inverse or cot inverse. So now let us take the next problem, that is L inverse of cot inverse of s. So even if you have a cot inverse or tan inverse, we can take the help of this inverse Laplace transform of derivatives, and by using that formula, by using that concept, we can find out the inverse Laplace transform of tan inverse or cot inverse. Follow the same procedure here. You, whatever the function he has given inside this L inverse, you consider that as f bar of s. So L inverse, so we have two methods here. So whatever the problem we have discussed in the previous problem, in the previous slide, so that is one method, method 1. Now we will go for the method 2 here. How can you find, so procedure to find out that inverse Laplace transform for this. So here L inverse of cot inverse of s. So once if you observe this one, this is of the form L inverse of f bar of s. So what is L inverse of f bar of s? We can consider that value is equal to f of t. So now I am considering this cot inverse of s. I will consider that as f bar of s. So L inverse of cot inverse of s is equal to, so whatever we apply for L inverse for the function which is in terms of s, you will get that value in terms of t. So we consider that value as f of t. So L inverse. So now you send this L inverse to this side. You send this L inverse to this side, you will get Laplace transform of f of t is equal to cot inverse s. So if you send this L inverse to this side, you will get Laplace transform of f of t is equal to cot inverse s. So now we have the formula Laplace transform of t into f of t. So we have the formula Laplace transform of t into f of t is equal to minus d by ds of cot inverse s. So derivative of cot inverse, we can take minus 1 by 1 plus s square, that is 1 by 1 plus s square. Now you send this to this side. So t into f of t is equal to L inverse of, if we send this L to this side, it becomes L inverse of 1 by s square plus 1. So 1 can be written as 1 square. So this can be written as sin t. So f of t is equal to sin t by t. So we can take f of t is equal to L inverse of that. So L inverse of, what is the function we have considered for f bar of s? That is cot inverse. Cot inverse s is equal to 1 by t into sin t. So this is another way how we can apply this inverse Laplace transform of derivative here. Now let us take another problem here. So inverse Laplace transform of tan inverse of s a by s plus cot inverse of s by b. So in this we are having both tan inverse and cot inverse. So we can follow any one of these two methods what we have discussed in the previous slides. So as usual, you consider this entire function as f bar of s. I want to explain this in method 1. So f bar of s is equal to tan inverse of a by s plus cot inverse of s by b. Now apply a derivative on both sides with respect to s. D by ds of LHS, d by dh of this both RHS terms. So now derivative of f bar of s, we can take that value is equal to f bar dash of s, and derivative of tan inverse, we have the formula derivative of tan inverse x is equal to 1 by 1 plus x square into derivative of that x. So here 1 by 1 plus x square. So here x is a by s, so a square by s square, and derivative of this value here, derivative of a by s minus, so plus minus derivative of cot inverse x. So you will get the same value, that is with minus sign different. So minus 1 by x square into derivative of that function. So you will get this. Now simplify this. So derivative of a by s. So a is constant, so we can take, and the derivative of it is of the form derivative of 1 by s, which is of the form derivative of 1 by x. So derivative of 1 by x, we can take it as minus 1 by x square. So here you will get minus 1 by s square. Same here, the denominator is constant, so keep the denominator and apply the derivative only for s. Derivative of s with respect to s is 1 into 1 by b, 1 by b. So now simplify this, you will get this value. So finally you take minus common from this. So this is our f bar dash of s. Now apply L inverse on both sides. So L inverse of f bar dash of s is equal to L inverse of these two terms. Keep minus sign. And L inverse of f bar dash of s, we can take it as minus 1 into t into f of t is equal to minus L inverse of 1 a by s square plus a square, this can be written as sin at, and b by s square plus b square, this can be written as sin bt. Now we want only f of t, so you send this minus 1 into t this side. So you will get f of t is equal to, already here we are having minus, so we can cancel this minus and minus. So it becomes plus 1 by t into this. This f of t can be written as L inverse of f bar of s is equal to this value. Okay, so this is the way how we can apply this inverse Laplace transform of derivative formula to find out the inverse Laplace transform for the logarithmic functions, as well as whenever we are having a function in terms of tan inverse or cot inverse. So this is the way how we can use this one. So in this video we have seen how to apply this inverse Laplace transform to find out the inverse Laplace transform of f bar of s, which are in terms of logarithmics and in terms of inverse trigonometric. In the next video we are going to discuss about convolution theorem in the inverse Laplace transform. What is convolution and what is convolution theorem, where you can use this convolution theorem in the Laplace transform or inverse Laplace transform. These things will be discussed in the next video. Thank you.